Yeah, thank you very much, Olivier, for this very kind introduction. And first of all, in the role of the organizer or co-organizer of this symposium, let me thank all the speakers and the audience. It's really been a pleasure to hear your talks and to hear these really lively discussions. In the role of the speaker today, I want to show you how to read between the lines of electronic spectra, namely the diagnostics of fluctuations in many-body strongly correlated systems. And this talk is based on two basis papers, namely the seminal paper of 2015, which I've referenced here, and a recent review of myself and Alessandro Toschi, which we wrote 2 years ago, and will cover most of the things I will speak in my talk, except for the very last part. So let me thank first, so to say, the original crew of this enterprise, namely Uli Gunnarsson from the Max Planck, Alessandro Toschi, Georg Rohringer, Emmanuel Gull, James Leblanc, Giorgio San Giovanni, and Jaime Merino, with which we started this endeavor with these two seminal papers, Fluctuation Diagnostics and Parquet Decomposition, which I will address in my talk. So what is this talk about? Well, it's about a very basic thing in many particle physics, namely how can we address or how can we obtain properties of many particle physics systems. And one of the basic things is also experimentally to do scattering experiments. We can do this at the one particle level, which is simply depicted here. You shoot in one particle into a system, let it propagate and interact with the constituents of the system and take it out again. And experimentally, this is very often realized by STM, inverse photoemission spectroscopy, or angle-resolved photoemission spectroscopy, where we had one really beautiful example as the very first talk of this symposium series by Anna in November. The point here is that I can get not only such beautiful Fermi surfaces like in the strontium-ruthenate, but also frequency-dependent spectra like hourglass phenomenon, Fermi arcs, or waterfall features. And in this talk, I want to focus a bit on these Fermi arc features, which shows up, for example, in high-temperature superconductors within the so-called pseudogap phase. And the pseudogap phase simply means that we gap out excitations of the spectrum at some parts of the Brunner zone or at some momenta and not in other parts, which results in these beautiful arcs. And the question is, okay, we can now measure this single particle level spectra. However, the question is, how does the system become excited in such a way? If you would ask myself the question, how I get excited, this would be very simple, and Antoine knows the answer. I would get excited with some beautiful wines like this very special bottle here. But the question is not so easy, actually, in the case of many electron systems. And especially the pseudogap has been attributed, for example, to spin fluctuations, to pairing fluctuations, and even to charge fluctuations. So the question which I want to answer today is, how can we identify the underlying physics of this one particle level spectra? Experimentally, we can raise the level of complexity in performing two particle level experiments. So we shoot in two particles into the system, let them propagate and interact and take them out again. Examples would be NMR experiments, where I have brought an example to you here. So you have a magnetic excitation, which is quite well defined about the antiferromagnetic point here, which may or may not lead to the pseudogap feature observed in, for example, high temperature cuprates. Turning now this idea of this two particle level spectroscopy into theory, what shall we do? And this is the essence of my talk. So after this introduction, I will introduce to you the basic model for electronic correlations, the Hubbard model. I will argue that there we can also calculate two particle level quantities which govern the linear response. And having these two particle level quantities by hand, we can tackle the problem of the interpretation of single particle level spectra in two general ways. One would fall under the class of Parquet decomposition. I will introduce the Parquet equations and describe the methods. Then I will show some examples of this, and then I will argue that this method breaks down at the strong coupling regime. I will also give reasons for that. And then in the second part of my talk, I will define what I mean by fluctuation diagnostics in the narrow sense, namely a change of perspective in introducing partial sums of the Dyson-Schwinger equation of motion. Again, I will bring some examples, and then I conclude with a general perspective. So the model, obviously, all of you already know in this symposium series. So this is the Hubbard Hamiltonian, which just contains one electronic hopping part and a local modelization of the Coulomb interaction. And in this talk, I will talk about only the one-band Hubbard model and mostly in 2 dimensions. I will show some results from diagrammatic Monte Carlo, so a numerically exact technique, and from quantum embedding methods like dynamical mean field theory and dynamical cluster approximation, as well as diagrammatic extensions of DMFT, the so-called dynamical vertex approximation. And more information about the techniques you can find in these reviews here. So how can we now describe theoretically the processes which I've introduced to you before experimentally? Well, on the single particle level, we will introduce some labels of real space positions and imaginary times. Obviously, if you want to describe this process, what I need is the so-called single particle Green's function, which I've shown you here, which exactly describes this inserting of a particle and taking it out. And we can calculate this dynamical amplitude with this so-called propagator. We can now apply Fourier transforms and time translation invariance, which gives us a 4-index object, a 4-index Green function with 3 indices about momenta and 1 index about, in this case, Matsubara frequency. Out of this Green function, we can calculate the one-particle spectrum, namely in taking the imaginary part of the retarded Green function if we analytically continue it. Let's go a bit into diagrammatics because we need this for this 2-particle level. So the basic constituents of our diagrammatics here is the free propagation with momentum k, the so-called free Green's function, and the local Coulomb interaction. I can build up now my interacting propagator, the interacting Green function, by invoking the Dyson equation. So I let the particle propagate without any interaction with the system, with 1 interaction, 2 interactions, and so on. I can resum this series and end up with the so-called Dyson equation with the self-energy as basic building brick, which we call one-particle irreducible part. I can raise now the level of complexity, as I've said before, by having 2-particle spectroscopies. So I have now 4 points where I insert or take out particles. I can now calculate or write down a transition amplitude for this, which is usually called the 2-particle Green function. I can again Fourier transform this. I have to choose a certain frequency convention, in this case, particle Hall convention, and I invoke time and translation invariance. Then I end up with an object which has 3 4 indices, namely 3 different momenta and 3 frequencies, which we usually call the 2-particle level Green function. This I can split into a connected part and a disconnected part. And the connected part, if I amputate all the external Green functions, the essence of this is what we call the full vertex F. So you can view this as a scattering amplitude at the 2-particle level. And if you want to connect this, for example, with experiment, well, I can close the legs again. I can calculate physical susceptibilities in different channels, for example, the charge, the spin, and the parent channel, in having one bubble contribution, which comes from the disconnected part of this 2-particle level Green function, and then the so-called vertex correction part. So how can we now connect this 1 and the 2-particle level? And there is one very direct connection, the so-called Dyson-Schwinger equation of motion, which is an exact relation which connects the self-energy on the left-hand side with the Hartree part and the part which stems from the full vertex F, which we can calculate from the 2-particle level Green function. So diagrammatically, this is depicted here. So how can we now tackle the complex problem of identifying the physical reasons for single particle level spectra? By analyzing this Dyson-Schwinger equation of motion. If we have we have access to this 2-particle level Green function. And one very clever strategy, which worked for more than 2,000 years, is to rely on Latin mottos. So we have 2 mottos in the talk. One is divide et impera, so divide and rule. The other is mutatis mutandis, so change what has to be changed. So the first rule is, or the first motto is very simple. I divide my problem, my very complex problem, in easier problems, which I can tackle separately. For example, this big Roman army here. and maybe this, the possibility of success will be then higher. The second possibility is, I will come to this in the second part of my talk, that I change the perspective on looking at the problem at hand. And by changing the perspective, I can go maybe to a simpler description as I had before. For example, the description of the solar system is much easier if we put the sun in the center. But first start with the divide et impera. So how can we now subdivide our problem, which we had before, and tackle these subsystems? And what we can do is we can take this introduced full vertex and divide this full vertex via the so-called Parquet equations. So the full vertex are all connected to particle level diagrams, which I've shown you before. It can be seen as a scattering amplitude. This relation, so the Parquet equation, are exact and unique. So we can divide this full vertex into a so-called fully irreducible vertex and reducible vertices in different channels. For example, particle-particle, particle-hole, or particle-hole transverse. They, in turn, can be linearly combined to obtain, again, our famous charge, spin, and particle, so pairing channels. And what does now mean this reducibility at the two-particle level? Well, I can, at the reducible diagram, I can cut two fermionic lines, and the diagram will fall apart in two. So I will separate these entries 1, 2 from this exit 3, 4, for example. I have three possibilities of doing this at the two-particle level. Hence, it's defining me three different channels. I cannot do this in any way at this so-called fully irreducible vertex, which we call lambda here. Just one comment about this Parquet equation. So there was no Monsieur Parquet who invented these equations, but it's really about the Parquet floor, which we also use in modern or not so modern dancing, for example, here at the Chateau de Versailles. Going back to physics, we take now this Parquet equation, we insert it into the Dyson-Schwinger equation of motion in our different channels, and then we can do all the summations, which we have to do in order to obtain a self-energy. But now the self-energy has different parts, namely one part which stems from the fully irreducible vertex, one from the particle-particle channel, the charge channel, and the spin channel. And like this, we can separately analyze the different contributions to the full self-energy. So let's give an example. And I take an example here, obviously the Hubbard model in DMFT and in DCA with 8 sites. And we can now define a certain test bed, for example, the 3D cubic lattice in DMFT, half field at a certain intermediate interaction. And what you see here is the exact self-energy, which we can directly calculate as the solution of the DMFT, which is hidden here as this black line. And it's good that it's hidden, because what's above is the sum, namely the sum of all the different contributions, which agrees with the exact summation. So this is some sort of consistency check here. But then what we see is that the biggest contribution to the self-energy here is already coming from the spin, which is indicated in red here. And charge and the particle-particle seem to screen, so to counteract to this self-energy in this contribution. And there is also one contribution stemming from the fully reducible vertex lambda. We can do the very same in the DCA if we have access to the two-particle level green function. We can take let's say the antinode here, so the K points pi 0, at some doping value and a fairly intermediate interaction of U equals to 4t. We can do the very same decomposition, and we arrive at least in this decomposition at a similar conclusion. Obviously, what we want to do is to go to stronger coupling, but I will show this in a minute. A second example, which we put forward in our PRX paper first, so the basis of this calculation was done there, and then the analysis in our review. What we did there is we analyzed the two-dimensional Hubbard model at fairly low interaction, again at half filling and on a simple square lattice. And I've put the phase diagram, the physical phase diagram here. So at t equals to 0, you see an antiferromagnetically ordered state. At finer temperatures, obviously, the order is forbidden by the Merman-Wagner theorem, but nevertheless, you get a very interesting sequence of crossovers coming from high to low temperature. And this we see actually also in the self-energy. So I've brought you here two self-energies for two different momentum points, namely the antinodal and the nodal point. And going from high temperatures, we see that we have a divergent behavior, which is resembling the atomic limit and is standing for not yet formed quasi-particles. But if I go to lower temperatures, we see that at the node, we first get some sort of coherence, namely that I can expand this self-energy in a Taylor expansion for the node, but not for the antinode. Then at even lower temperatures where we have the metallic phase, I can expand it for both. And if I go even lower in temperature, I can see again that spin fluctuations, so the correlations close to the ordered state at t equals to 0 kick in. I gap out first the self-energy at the antinode, and then in both the node and the antinode, I get an insulating state. A very nice observation also here is we could calculate within the dynamical vertex approximation the magnetic correlation length, so the antiferromagnetic correlation length, and it behaved at low temperatures exponentially, so an exponential growth, as you would expect for this recoupling regime. But we also found a different exponential within this metallic regime, actually, with a different slope, as you can see here. This was also very nice because we could connect this exponential growth with this one particle level with a criterion which was introduced by Wilk and Tremblay, which we call the Wilk criterion, namely condition for a pseudogap at weak coupling, namely when this magnetic correlation length is much larger than the thermal de Broglie wavelength, we open up the pseudogap, so we see the footprints of the spin fluctuation in all observables. But nevertheless, these two slopes were pretty interesting to us, so we went one step further and analyzed the self-energy within these three different regimes. So at very high temperature, at this incoherent regime, we see that both actually the rest, which we call, so this is the particle-particle and the irreducible part, as well as the spin fluctuations, are contributing very much to this let's say incoherent self-energy. If we lower the temperature, we see that this is now a differentiated plot between the antinode and the node at the bottom. We see that for the node, we don't have, or we have a self-energy which is actually Fermi-liquid like in both, so at the antinode and at the node. But at the node, we see that also only the spin part is exhibiting this metallic-like behavior, whereas in this regime, already the antinode is showing some very non-metallic behavior for the spin contribution. So this is true only in this metallic regime for one of this, so for the antinode, where it is true for both the node and the antinode at very low temperatures, which could indicate that, okay, these regimes are quite different because here both momenta are gapped out in the spin sector. Coming back to the original method, so to the Paquet decomposition, we saw this Paquet decomposition worked pretty nicely at low to intermediate coupling. However, if we increase the coupling, we see that we get this very strange and very heavy oscillating features in some parts of this Paquet decomposition, namely in this case, the irreducible vertex part, as well as in the charge sector. So here it's really difficult to interpret these different contributions to the self-energy, and the Paquet decomposition breaks down in a certain sense. Why does it break down? Why is it so chaotic? Well, this we also analyzed, and we know that these Paquet equations, although the full vertex is well behaved, the different components of this Paquet equation, namely the fully irreducible vertex, as well as some of the reducible parts, show divergences at low frequencies, which have a lot of consequences, actually, be it methodologically or even physically. But it also leads to a breakdown of the Paquet decomposition as a usable decomposition for this self-energy analysis. So what is the way out? One way out would be that we change the type of summation. For example, we could sum all the other channels except for the spin, which we called beta-salpeter summations. And this behaves, again, nicely, but we cannot separate now, for example, the charge from the particle-particle and so on. Another way out was introduced by Friedrich Green and co-workers, namely they introduced a different decomposition of this full vertex F, namely not into two-particle reducible and irreducible components, but in interaction reducible and irreducible components, where these vertex divergences do not show up actually. And this could be used as a stable Pachet or not Pachet decomposition, but single boson exchange decomposition and analysis for the self-energy. However, what I want to show in the second part of the talk is quite another way out, namely mutatis mutandis, change what has to be changed. And this is what we call the fluctuation diagnostics in the narrower sense. What is it about? We go back to the Dyson-Schwinger equation of motion, which I've introduced in the first part, and we see that what we have to do here are quite many summations, namely on the internal momentum and frequency and the transfer momentum and frequency here, because these are 4 indices. This is the first observation. The second observation is for an SU2 and U1 symmetric system, as we have, for example, in the pseudo gap of the DCA, we can rewrite this equation of motion with introducing the full vertex in the spin channel, which has this up full vertex, which due to this SU2 symmetry and some crossing relations drop out of the equation. So we can simply, so to say, smuggle this part in. We can do the very same in the charge, which is a linear combination with a plus here in the middle, or we can do a frequency shift, which results in the particle-particle full vertex. So the point is now that if I do all the summations in this equation, these are equivalent and give the very same results due to SU2 symmetry and crossing relations. However, the point is, what about now partial sums? So if I omit some of the sums, can I get interesting information about the system via this? So what I can do is, I can, for example, omit the sum over the transfer momentum Q, which is hidden in this small q here. And I can then have a momentum resolved quantity, which we call the sigma tilde Q, in a certain channel. For example, the spin, but also the charge and the particle-particle channel. I can, on the other hand, omit the sum over the bosonic frequency, and I can then write down a frequency resolved sigma, the sigma tilde I omega n, by omitting the frequency sum here in these different channels. And in the slides to follow, I will show that this momentum resolved quantity in histograms, where we will show the frequency resolved one in pie charts. So let's check what we can obtain, which information we can obtain from a system where we know what is going on. And this would be the attractive Hubbard model, where we expect that charge and particle-particle fluctuation are dominant. We applied now the DCA for 8 patches in a particle asymmetric case, so for 13% doping at an intermediate temperature for an attractive U, which is also intermediate. Here we obtained a self-energy for the antinode and the node, which are both metallic-like. And what we could do now is, for the first frequency of these self-energies, analyze in these different representations from which momenta the self-energy stems from. For example, I can decompose or write this Dyson-Schwinger equation of motion within the spin channel. And what I see in the spin channel is that the contributions to the full self-energy split into the separate momenta are more or less equally distributed. So this is maybe not a good perspective to look at the situation. A better perspective would be, as it's indicated by this histogram plot, to look, for example, in the charge sector, because I have a very well-defined mode in the charge sector, which gives a quite large contribution to the self-energy, namely the pi-pi one. The same is true for the particle-particle sector, which gives a large contribution, a well-defined mode, if you wish, for the Q equals 0, 0. So the same is true actually also in the frequency picture, where I can write the frequency contributions to the self-energy in a pie chart, and you see that in the charge as well in the particle-particle picture, most of the contribution is actually coming from the omega equals to 0 contribution, which means that we have, first of all, well-defined, this we know via the momenta, and second, long-lived excitations, which are driving the physics here. So the charge and the particle-particle fluctuations are well-defined and long-lived. Let's go to another example where we have not known what is really going on, namely the pseudo-gap phase of the repulsive Hubbard model. And I will argue that with this method, we could determine the origin of the pseudo-gap in this model. So we set some parameters for the 2D Hubbard model, where in the DCA we get the pseudo-gap, and the indication for this is that for the antinodal patch, you get the divergent self-energy, which means that you kick out the states here at the antinodal direction, whereas you keep the states in the nodal direction, which eventually will result in Fermi arcs. How is the histogram now looking like here? Well, it's a very clear-cut situation, as you can see, whereas before in the attractive model, we had both charge and particle-particle fluctuations, which were dominant and which were clearly defined. Here, it is the spin fluctuation, which is clearly defined, namely the spin fluctuation at the pi point, which are antiferromagnetic spin fluctuations. So in a certain sense, the spin wins because the charge and the particle-particle fluctuations, as you can see here, are equally distributed over all momenta. So they don't represent a very good perspective to look at the problem. They are not well defined in a certain sense. If we go now to the frequency resolution, we see again, the spin picture is really dominated by the omega equals to 0 contribution, which means that we have long-lived excitations. However, in the particle-particle as well as in the charge sector, we get the distribution among many frequencies, which means that we are unfortunately short-lived, or fortunately. So the spin fluctuations are responsible for opening up the pseudo-gap, as we could show in the seminal paper. There have been many papers afterwards who clarified many aspects of this problem. For example, this very nice work of Emanuel Bull's group, where he did a doping study basically of this problem again within DCA. And what you can see here that again in the charge picture, you don't have the histogram here, but you have a whole distribution because you have many doping levels here. You see that within the charge perspective, the contribution to the self-energy is distributed among many momenta in an equal manner. Whereas in the spin picture, it's really the pi-pi mode, which is the strongest contribution to the self-energy. If we now change even the method which we use to solve the Hubbard model to an numerically exact technique like diagrammatic Monte Carlo, Wei Wu and co-workers could show that you even can lift there the discrete momentum patches and have a continuous momentum distribution. And for this point, which is famously called the waypoint internally, you have the pseudo gap here in the self-energy, as you can see. And you can clearly identify that within the spin picture, you get a clear mode, so a clear enhancement of, let's say, the scattering, a big contribution around the pi-pi point at the antinode, also there. So even in numerically exact technique. And there were many other works following this route for the normal state of the Hubbard model. What I want to discuss now in the last part of my talk is a method which actually went beyond the normal state and entered the superconducting state of the two-dimensional Hubbard model. So there, the fluctuation diagnostic in the narrower sense was applied, let's say, to the anomalous self-energy, which you only obtain if you're entering the U1 symmetry broken phase. And this was the work of Xingfang Dong, Lorenzo Del Rey, Alessandro Toschi, and Emanuel, who did the brave task of generalizing the equations which I've shown you before for the fluctuation diagnostics and the Dyson-Schwinger equation of motion from this U1 and SU2 symmetric situation, where we clearly identified the charge part, the spin part, and the particle-particle part, to the situation where the U1 symmetry is lifted. And what happens there is then that you get common channels, first for the charge and the singlet pairing, and then for the spin and the triplet pairing. So you lift this division, so to say, of charge and singlet and spin and triplet here. If you go through all the equations, which I guess was a quite heroic task to do, you end up at similar equations to what we had before for the fluctuation diagnostics, namely Dyson-Schwinger equations of motions, where you have a lot of sums in it, and you can then lift partial sums. This is what they did. And this is now for the two-dimensional square lattice Hubbard model again, for some parameters as a function of the doping. And for the doping, they took two very representative points, namely one in the underdoped phase, where you are actually in the ordered phase, and one of the overdoped phase. They analyzed the anomalous part of the self-energy, again the first frequency, at the antinode. And now this is some sort of a mixed notation here. So what we first had separated in histograms and pie charts is now only one pie chart. But if you take a look at the magnetic channel, you will immediately know what I mean. So you have the pi-pi contribution as the momentum contribution, and within the pi-pi, you have here the several frequency contributions within this one pie chart. And what you see is in both the underdoped as well as in the overdoped regime of the two-dimensional Hubbard model, you see a well-defined mode in the magnetic triplet channel, which is actually governed by the pi-pi. So again, antiferromagnetic if you wish, and a very low frequency. So in this case, the zeros frequency, which is the dominant one. On the other hand, in the density or singlet channel, you have an equal contribution or distribution among several frequencies as well as several momenta. So also here, the magnetic channel seems to drive the pairing. We can take a closer look. For example, if we plot the different contributions to this anomalous self-energy from different momentum patches of the DCA, whereas in the density representation, you can see that all the contributions are more or less equal. In the magnetic triplet representation, you see that the largest part, again, is coming from a well-defined mode, which is the pi-pi mode. So the antiferromagnetic spin fluctuations, which serve as a pairing glue, whereas the ferromagnetic one, so the uniform fluctuations, are counteracting to this. In a certain sense, this is again spin fluctuations which drives the physics, but of a different kind than at weak coupling. The reason for this, that I'm saying this, is in this work by Shanfang Dong, Emmanuel, and Andy. There was a comment there that about only half of the superconductivity can actually be attributed to the pairing glue in a standard one loop theory. So you have to go beyond the one loop in a certain sense to stronger coupling to obtain the full strength of the superconductivity. So with this, I'm already at the end of my talk. I provided you with general strategies for the insights in the origins of correlated spectra of strongly correlated electron systems with the abuse, so to say, of the Dyson-Schwinger equation of motion, where you need as a prerequisite, obviously, the 1 and 2 particle level green functions. In the Parquet decomposition, divide ad impera, we saw that we can subdivide the full vertex within the Parquet equations to get quite directly a distribution of the different contributions of the channels. However, it got unstable for increasing U. In the fluctuation diagnostics, in a narrower sense, so mutatis mutandis, we changed the perspective in taking a look into our system via different representations of the Dyson-Schwinger equation of motion and doing partial resummations. So we saw this is a very versatile tool. Actually, we can use different numerical techniques as long as they are unbiased, and we have access to the 2 particle level green function. And this is the reason why there were quite many papers following the original one in the recent years. But obviously, we have to take a look at the future as well. So what we want to apply this technique to our multi-orbital systems, for example, iron-nictides, we have to include somehow non-local interactions. and maybe directly connected to also research efforts at the flat iron. A good question is, how can charge fluctuations, which are seen actually within the pseudo-gap phase at lower temperatures, be detected in the single particle level spectrum? So with this, I just want to advertise again shamelessly this review, which tackles a lot of problems which I've advertised in my talk. And thank you for your attention.
Thank you very much, Thomas, for this very nice talk. We now have a couple of minutes left for questions. Is there questions? Can you people raise hands? Antoine has a question. Let's start with that.
Good. Hello, can you hear me? Yes, beautiful talk. Thank you, Thomas. This fluctuation diagnostics, I think, brought a lot to the field. I have a question which is perhaps a little less related directly to your own work, but of general interest. And you mentioned at some point the single boson exchange, right? So can you briefly explain again how the fluctuation diagnostics would work in that case, and perhaps also why the singularities do not appear?
Yeah, so to my understanding, the singularities do not appear because of this different splitting, or different, so to say, different splitting of the full vertex, basically. Because
so it's a statement about the 3-leg vertex, which doesn't have the same singularities as the 4-leg ones. That's the thing.
So the point is that you split your diagrams into interaction reducibility, right? So not
right, but it involves the triangular vertex as compared to the box one.
Yeah, absolutely. There, I mean, what you could do then there basically is just, I would say, some sort of similar decomposition, or you're doing a similar decomposition as the parquet, where you sum again over your higher order diagrams to obtain your self energy, I guess. So there you
and so what you are saying is that the fluctuation diagnostics has been applied in this decomposition as well.
Yeah,
I see. Very nice.
Yeah. Thanks. Next question is by Walter Metzner.
Yeah, hi. So yeah, first of all, thanks for this very nice talk, Thomas. And personally, I fully have share this opinion that in the Hubbard model for sure, and probably also in the cuprates, spin fluctuations are both the main player for the pseudogap and also for the pairing. But there are still a number of people, especially my old friends in Rome, Di Castro and etc., who very much emphasize charge fluctuations. And so I wonder whether maybe in the 3-band model, there's more room for the importance of charge fluctuations. And of course, in principle, you could analyze this. In practice, it's for sure not easier than doing this for the 1-band Hubbard model. Do you have some insights here or some plans?
Yeah, so first of all, what we want to do is to go to the Emery model very, very soon. And I think this is a first step of the full interacting cuprates. The second thing would be very nice, which I briefly addressed in the very last part, because we also see in the Hubbard model that well inside the pseudogap phase, we also get this tendency towards charge ordering or increased charge fluctuations. And
but more as a secondary effect, probably, right? Right.
Yeah. And this, however, it's secondary, but it would be nice also to penetrate also this regime, so to say, with an unbiased technique, and see whether, you know, some parts of the self energy could be maybe attributed to this stronger charge fluctuations even there.
Okay, thanks.
Thanks. Next question is by Scha.
Can you hear me?
Yes.
Okay, great. Yeah, hi Thomas, great talk. Coming back to all the spin fluctuation but strong coupling. So you mentioned this paper by Andy Millis, and Andy is here, maybe he can comment, but still 50% is strong coupling. Can you say what is this 15%? Because I'm not sure that if you really go to this U = 6 is already strong coupling. And of course, you say that this is a spin channel. That's true, but it's not tell you that this is spin fluctuation. It's very different things, yeah? That you have divergence in spin channel and spin fluctuation. For example, we discuss with you guys, and I remember Tosi. So, you know, Ole Gunnarsson did both spin fluctuation and cluster DCA, 8x8 or even 16x. And he sees that in a cluster DCA, the effect of a pseudo gap, he even mentions this, that this is related with destructive interference. Yeah, this is not spin fluctuation.
Right. So what I mean with
what you can say?
Yeah, so I mean with this argument, and maybe Andy can or cannot, due to technical reasons, comment on that, is that in this paper, as far as I know, they tried to calculate this pairing width in this one loop, right? And there it could only attribute to a certain part. Where this part stems from, I'm not so sure, but Andy's I think managed to.
Yes, Andy can comment.
Yeah.
Right. Well, if I may interrupt, thanks. Yeah, for some reason, logging out and logging in again worked. So that was, anyway. So look, I don't have a real answer. Let me give you some more or less poetry. The two clear statements that come out of Emmanuel's two 2022 papers, the one with me and the one with Alessandro, are that the spin fluctuation channel is what's really responsible for the superconducting pairing, and that the low frequency spin fluctuations, the things that might show up as, you know, antiferromagnetic paramagnons in a neutron scattering experiment, do not give you more than sort of half the pairing amplitude. Therefore, one would conclude that there is some kind of high energy but spin-related pairing process, which is important in the model. So personally, this is the poetry part. I like to think of this in terms of Anderson's original RVB idea. That you have a short-range, high-energy exchange that just wants to make singlets, and that's really what's going on. But I would say that at this stage, this is still just poetry. At least we were unable to come up with any direct evidence for it, but it seems nice and plausible.
But question is, do fluctuation diagnostic can distinguish this?
Well, I mean, in the full vertex, you should have the information about this, right? So I guess yes, and maybe connected to your previous statement. So I'm not sure about the real barrier between weak coupling and strong coupling in terms of the interaction, but we have some indications also of the work of Wei Wu and Michel Ferrero and Antoine, that around U7 within this DCA approach, right, there is a strong increase of correlations, and there is a very sharp boundary between weak and strong coupling. Admittedly, maybe U6 is maybe not enough. Yeah.
Yeah. Well, it would be interesting to push the analysis that Xinruan, Emmanuel, and I did, both the stronger and to weaker coupling. Our paper was really specifically U = 6, and it was mostly because we had a lot of data lying around for that particular.
Right. Yeah, it would be worth it, I think. Yeah.
Okay. Antoine wanted to ask one more thing.
Yeah, maybe just to add poetry to poetry. If we leave for a moment the superconducting state, but just go slightly above into the pseudogap normal state, then we can, of course, complement the fluctuation analysis of the type that Thomas talked about to an analysis in terms of multiplets of histograms, right, which contribute to the state of the system. We can also do that in the superconducting state, I guess, and we would definitely see what Andy is saying, namely that a large part of the wave function is dominated by short-range singlets on the cluster, right? So I guess those guys would manifest themselves more like as a high-energy contribution to these fluctuation diagnostics, maybe not immediately discernible, but at least this is consistent.